This is a video for Polynomials Day 5, which is Polynomial Identities. We're going to start with a warm-up, which is some good review. So grab some paper, and you can take a second to pause the video and try these couple of problems to practice your multiplication. So go ahead and pause the video and give these problems a try. Okay, so if you've multiplied all these out, say using our box method for the 2 by 2 and the 2 by 3, right? This is what you should end up with. So x plus y times x minus y, right? X squared minus y squared. Multiply these two things together, the binomial times the trinomial, right? You end up with x to the third plus y to the third. The other binomial times the trinomial should get you x to the third minus y to the third. And we're going to come back to that in our notes, but that was good practice of some of our multiplication there. Okay, so let's take some notes. There we go. Okay. So Polynomials, Day 5. And again, this is Polynomial Identities. Polynomial Identities. So, an identity, we may have used that word before, perhaps earlier in the year. You may have talked more about it in algebra as well. So an identity is an expression that is always true. Okay, an identity is an expression that is always true, regardless of whatever the value of x is. Okay, so regardless of x values. So identity is an expression that is always true regardless of x values. So those couple of things that you actually just multiplied out in the warm-up, these are actually examples of identities. Because no matter what x and y are, right, when you do x plus y times x minus y, you always end up getting x squared minus y squared. We just sort of proved that algebraically. So that's an example of an identity. So identities we know, and there's actually quite a few of them that pop up in various situations. But we can take those couple from the warm-up. The other place we saw these, by the way, is when we did our factoring. Right? So we learned when we did factoring that when you have something that's in the format of x squared minus y squared, you can factor it into x minus y, x plus y. So again, that's using that identity, the fact that that's something that's always true no matter what x and y are. Okay, so these are really our factoring formulas, right? X to the third plus y to the third. And remember from our factoring unit, that's the sum of perfect cubes. Right, so that factors into the binomial x plus y, and then the trinomial. Right, so x squared plus minus plus, so minus, multiply them together, right, and then square the second one. Right, and that is something that, again, is always true. And the same thing for the difference of cubes. Right, so that factors into x minus y, and then it would be x squared plus xy plus y squared. So yeah, we use those formulas when you're factoring, but really they're identities because again they are always true, and we just proved them and in that warm-up when you multiplied them together. So sometimes you might come across a problem where they might give you another identity and have you verify that it's true. Okay, so we're going to verify that x plus a quantity squared minus x minus a quantity squared is equal to 4ax. Right, so we want to verify that that is an identity. Right, so I want to verify that this expression, equation, right, is an identity, meaning that it's always true. So if we want to show that this is always equal to that, and we can do, what we're really doing is a proof. I know the proof, takes you back to geometry with the statements and the reasons. This is a different kind of proof, and it's an algebraic proof. So I want to show that both sides are equivalent to each other. So I'm going to draw this imaginary line kind of down my equal sign. And again, I want to show that the two sides are equal. So there's not really a lot I can do over here, but the idea is when I multiply all this out and do my subtraction, I should get this 4ax, and that's my job, is to show that. Okay, so I'm going to do this multiplication. I'm going to do our 2 by 2 multiplication over here on the side. And so if I multiply x plus a times x plus a, ax, all right, a squared. Okay, so that ends up being x squared, and then there's 2 of those ax terms, and then plus a squared. And so that's what that's equivalent to. Then I'm going to do x minus a squared. So we multiply that out. So x and negative a, x and negative a. So x squared, negative ax, and then it would be positive a squared again. Okay, but that's all getting subtracted, right? So I'm going to put this subtraction and then put a big parentheses there so that all of these terms go inside that. So x squared minus 2ax plus a squared. So close. Okay, but again, that's coming after this subtraction sign, right? So that negative would get distributed through. So I'm going to move this over a little bit, give myself some room. Okay, so when I take that negative and distribute it through so that all those terms are getting subtracted, so it's going to be a negative x squared, and then a positive 2ax, and then a negative a squared. Okay, so now if I go through and try to put some like terms together, right, you'll notice that quite a bit of this actually cancels. So this positive x squared and that negative x squared cancel, right, and then the positive a squared and the negative a squared cancel. So we're left with these two terms, which are both positive. So 2ax plus another 2ax would combine together to make 4ax. And then, lo and behold, that's exactly what we got over here on the other side. Right? So we just proved that this is an identity by doing some algebra. We showed that when you break this down, doesn't matter what value x and a are, right, you're always going to get this 4ax at the end. And again, so we just showed that. So how are these identities useful? We can actually use them to do some mental math. So here's some cool math tricks. So identities are helpful tools for doing mental math quickly. And I'll show you some examples of how we might use them. Okay, so this says use x squared minus y squared, right, equals x minus y, x plus y, so that identity that we saw up above, to evaluate, and we're going to use it to evaluate a couple of things here, right, starting with 50 squared minus 49 squared. And so if I told you to figure out 50 squared minus 49 squared without a calculator, right, you're like, I don't think I can do that, and I don't think I can really do that quickly either. But if I look at this and say, oh, wait a minute, this is actually the difference of two perfect squares, right? So I could sort of factor that into 50 minus 49, and then 50 plus 49. Using my identity, right? Because that's what it says, 50 squared, 49 squared, so I can break it down like so. But then wait a minute, what's 50 minus 49? That's just 1, right? What's 50 plus 49? That would be 99. And then, oh wait, multiply them together, right? And you end up getting 99. Right? And I can check this on my calculator and pull the calculator up here, right? Just to show you that when you do, right, 50 squared minus 49 squared, oh, hey, look, you get 99. Right? But we didn't even need the calculator. We were able to figure it out in our head. Right, so identities are useful so to do some mental math. Okay, how about if I wanted to figure out 51 times 49? Yeah, you could do it by hand, right? But I'd really like to do it, doing very little work as possible. So, noticing that 51 and 49 are both just one away from 50, right? 51 is one above it, 49 is one below it. So, couldn't I rewrite that as 50 plus 1 is 51, and then 49 I could rewrite as 50 minus 1. But now, that's like this side of the identity, right? So working backwards off of that, right, that would be equivalent to 50 squared minus 1 squared, right, which would then factor into 50 minus 1, 50 plus 1. I have it written the other way, but same thing. But now this is something I can do in my head. 50 squared, 5 times 5 is 25. Throw a couple of zeros on there. Right? 1 squared is 1. So therefore, 2,500 minus 1 should give us 2499. Right, I can pop over to my calculator to verify. Oops. 51 times, oh dear. Okay, 51 times 49, there we go. Okay, there it is, 2499. Okay, so said identities are helpful. We can use them to use some mental math should we find ourselves in a situation when we would want to do that. Okay, a couple more examples here. This one says prove that a plus b quantity squared is equal to a squared plus 2ab plus b squared. And then it says use it to calculate 35 squared. And so I want to use my identity to do that in a quick fashion. Okay, so again, if I want to show that this is an identity, my goal is to show that those two sides are the same. All right, so I'm going to draw my line down the middle there. So I'm guessing when I multiply out that a plus b squared, right, I'm probably going to get that. So, but I want to show that work. Again, this is a proof, so you want to make sure it's clear, where your work is coming from here. So I'm going to show my multiplication over here to the left. I'm going to do my 2 by 2 with the box method again. So this comes out to be a squared, right, and then combine on the diagonal to make 2ab, and then b squared. And then that's all, right? That is equal to that. So that was a pretty easy one. Okay. But again, you want to make sure you have that work there to justify where your answer is coming from and why you know that that's true. Okay, then we want to use this to calculate 35 squared. So how am I going to use that to figure out what 35 squared is? Well, basically what this identity is saying, right, is that if you have two numbers added together and squared it, right, then it's equivalent to this formula. So I want to take 35 and break it up into something that would be easy for me to do in my head. So maybe I'll let A be 30, right, and then B be 5. So then I could rewrite 35 squared as 30 plus 5 squared, right? That's the same thing. But then using that formula, right, so when I take my a plus b and square it, I should get this thing. So a squared would be 30 squared, right? And then 2ab, so 2 times 30 times 5. And then b squared, which would be 5 squared. And that's all stuff that I can, again, do pretty easily in my head. 30 squared, 3 times 3 is 9. A couple zeros there, 900. Okay, 2 times 30 makes 60. 60 times 5 would be 300, and then 5 squared is 25. So 900 plus 300 makes 1200, and then add another 25 on there. So we should end up getting 1225. Okay, so that's 35 squared using my identity. Now that's not the only way I could have done it, right? There's a lot of different numbers I could add together to make 35. So yeah, what if I let A be 20? Oh, 25 I did, right? So A could be 25 and B would be 10. So then I would really be calculating 25 plus 10 squared. And then again, using this formula, right? So that would be 25 squared, and then 2 times 25 times 10, and then plus 10 squared. But again, this is all stuff that I can do in my head. If you happen to know that 25 squared is 625, that one comes up fairly often. 25 squared is 625. Okay, 2 times 25 makes 50. 50 times 10 is 500. And then 10 squared makes 100. So 500 plus 100 makes 600. 600 plus 625 makes 1225. Right? So that's another way to figure it out. So, yeah, should you find yourself in this age of technology without a calculator and you wanted to do some mental math, you could use your identities to help you with that. Okay, the last place where identities come into play a lot is when we're working with right triangles and doing some Pythagorean theorem. All right, so at some point, you learned the definition of a Pythagorean triple. Pythagorean triple. You may have talked about this in geometry last year too. All right, so a Pythagorean triple, right, contains 3 integers, a, b, and c, that can form the sides of a right triangle. Okay, so Pythagorean triple contains 3 integers, a, b, c, that can form the sides of a right triangle. So how are you going to form the sides of a right triangle? Well, so say I have a right triangle, and my sides are 3, 4, 5, right? And I say, is that really a right triangle? Well, how do we know if it's a right triangle or not? It's got to follow the Pythagorean theorem. The Pythagorean theorem has to work. Right? So when we do a squared plus b squared equals c squared, it should work. So in this particular triangle, right, 3 squared plus 4 squared would have to equal 5 squared, which of course we know it does. This is the most common Pythagorean triple, right? But 9 plus 16 makes 25. So that works. So 3, 4, 5, that's a Pythagorean triple. All right, another common one is 7, 24, 25. So I say, okay, is that a Pythagorean triple? Well, when you do 7 squared plus 24 squared, right, does it come out to be 25 squared? And it does. As I said, this is another common one. So you can check it on the calculator, but it does in fact work. Okay, so that's another one. But it doesn't always work. Right? Like what if I wanted to make a right triangle where the sides were 1, 4, and 5? So if I tried to do Pythagorean theorem, 1 squared plus 4 squared, and say, is that equal 5 squared? So 1 plus 16 would be 17. That does not equal 25. All right, so this does not work. So that is not a Pythagorean triple. And so, and Pythagorean triples got to be able to work in the Pythagorean theorem, basically, so that it can form the sides of a right triangle. So we can bring some identities into this. Ever wonder how they figured out what those Pythagorean triples actually are, other than just testing them out? Right? Identities kind of give us a way to do that. So it says, given the following right triangle, okay, so I have a right triangle, oops, and its sides are 2x, x squared minus 1, and then the hypotenuse, right, is x squared plus 1. Okay, so given this right triangle, right, we want to show that 2x squared plus x squared minus 1 squared equals x squared plus 1 squared is an identity. Right, so where are they coming up with this? These are the sides of our right triangle. So if that's going to be a right triangle, then the Pythagorean theorem would have to hold true. So a squared plus b squared should equal c squared. Okay, so we want to show that. So like we've done in our other problems, right, I'm going to draw the wall. This one's got a little bit to it, right? I've got some work to do on both sides. But I want to work out again, both of those sides and show that they come out to be the same. Okay, so if I do 2x quantity squared, square the 2 and square the x, that's going to give me 4x squared. Okay, to do x squared minus 1 quantity squared, and do a little 2 by 2 multiplication over here. So multiply x squared minus 1 times itself. So that would be x to the 4th. A couple of negative x squareds in there. And then a positive 1. Okay, so the x to the 4th. And then minus 2x squared. And then plus 1. So then I do have some like terms I can put together there. So I'm going to end up with x to the 4th. And then a positive 2x squared. And then a plus 1. Okay. So when I multiply this out, I should end up getting that. So I'm going to scooch over here a little bit. I'll do it over on the side. Okay, so let me do my 2 by 2 multiplication for x squared plus 1 squared. Here, plus 1. So x to the 4th and a couple of positive x squareds. Okay, so that ends up being x to the 4th plus 2x squared plus 1. Okay, which is exactly what we wanted. All right, so again, I've got the work to show, right, that both of those things are equivalent to each other. So that means that this is true no matter what the value of x is, so that I proved that was indeed an identity. Okay, so now that we have that, we can actually use it to generate some Pythagorean triples. And so it says if x is equal to 3, what Pythagorean triple would this produce? And so if x were equal to 3, what Pythagorean triple would this produce? So, again, the identity says that 2x squared plus x squared minus 1 squared is equal to x squared plus 1 squared. So really what that is, right, is that's our a squared plus b squared is equal to c squared formula. So whatever's in these parentheses, right, that's got to be equivalent to a, right? Whatever's in these parentheses and gets squared, that's equivalent to b, and whatever's in these parentheses and gets squared, that's equivalent to c. So we can figure out what that is. So a would be equal to 2 times x, and x is 3 right now. All right, so a is going to be equal to 6. B is going to be equal to x squared minus 1. So 3 squared minus 1, 9 minus 1 makes 8. And then c is going to be equal to x squared plus 1. So 3 squared plus 1, 9 plus 1 makes 10. So we end up with this Pythagorean triple, right, 6, 8, 10. Which is in fact a Pythagorean triple, right? If you have a triangle, say that's another fairly common one, right? But if you think about 6 squared plus 8 squared, right, and does it equal 10 squared? It does, because 6 squared is 36, and 8 squared is 64, and 36 plus 64 makes 100. Okay, so that is, in fact, a valid Pythagorean triple, right? It works in the Pythagorean theorem, and we generated it by our identity. So we could generate as many as we wanted, right? What if x equals 2? That would give us another one. What if x equals 5? That would generate another one. And so that's how you can find more Pythagorean triples. Okay, last question. So this is not the only identity that would give us those Pythagorean triples. Okay, so another polynomial identity that generates Pythagorean triples, Pythag triples is, okay, so another polynomial identity that would generate Pythagorean triples goes like so. X squared minus y squared squared plus 2xy squared is equal to x squared plus y squared squared. Okay. And then the question is, what values of x and y will generate the triple 9, 40, 41, right, which is another one. Okay, so 9, 40, 41. And so I want to figure out what values of x and y would I plug into this formula so that it would produce, right, 9, 40, and 41. So I know this is just mapping out, you know, the Pythagorean theorem. All right, so A's got to be x squared minus y squared, B's got to be 2xy, and C would be x squared plus y squared. And then on the other side, they're giving me the final values of these, right? So A and B, I don't really know which one is which, but I know that the C has to be the biggest one, right? So that one has to be C because it's the hypotenuse and it has to be the largest. Okay, so C has to equal 41, right? And then these two, I don't really know which one is which, right? Either A or B, one of them's A, one of them's B. So I have the formula and then I have the end result, so I can sort of put these all together here. So if A is really equal to x squared minus y squared, right? But then in the end, I want that to be 9, right? And then the formula for B is 2xy, but then I want that to come out to be 40. And then C, the formula for that is x squared plus y squared, but then I want that to come out to be 41. And what I really just formed there, right, if I take off the ABC part, right, what that really just made is a system of equations. Right, and we can actually solve that system, some more good review here. Right, we've got several methods that we could use to solve a system of equations. Right, we could do substitution, or the elimination method. Elimination. You know, we've got multiple equations and we're only trying to solve for two things. So again, there's lots of ways that you could go about solving this. As I'm staring at it though, I'm noticing that, well, if I actually put these first two together, the minus y squared and the plus y squared would go away, and then I would have something that just would have x in it. So I'm going to go that route, although not the only way to do it. But say I put this first equation, x squared minus y squared equals 9, with the second one, or sorry, with the third one, x squared plus y squared equals 41, and do some elimination there, right? Put those together, my y squareds will cancel out, and then that'll just leave me with 2x squared, right, equaling 50, but there's just an x in there, so I can solve that if I divide both sides by 2, right, and get x squared is equal to 25. I'm going to square root. Right, now, we've talked a lot about how you're supposed to put a plus minus in. However, it's going to be a Pythagorean triple that represents the side of a right triangle. It's got to be positive. All right, so only positive 5. Okay, so that's the value of x. And then I just need to pick one of these to plug it into to then find the corresponding y. So I'm going to pick this one that doesn't involve any squaring, although you could pick any of them. All right, so 2xy must then be 40, and I know that x is 5. Times y would equal 40. So that would give me 10y being 40. So therefore, y must equal 4. So when x is equal to 5 and y is equal to 4, and I plug it in here, right, I end up getting this Pythagorean triple. So I'm just sort of working backwards there. Yeah, it's a good review of our solving systems. Okay, that's the end of these notes for Polynomials Day 5.